Welcome back, everybody, to the Python tutorial seminar series. Today, Drew Camron will be covering Metpy, and we're pleased to welcome him here today. Before I begin, we need to review the code of conduct. By joining this Zoom call, you've agreed to adopt these values and engage in respectful communication only. Any disrespectful or inappropriate remarks will have you removed from the call from one of our co-hosts. The seminar is only an hour long, so we may not be able to provide individualized attention to everybody, but we will do our best to respond to the chat, and there'll be time for questions afterwards. So please, if you have any trouble, sit back, relax, and trust that we will get to you. So your speaker today is Drew Camron. He works as a Python developer with Unidata, which is one of UCAR's community programs, where he serves as a maintainer for the open source Metpy and Siphon projects, along with Unidata's collection of synchronous and asynchronous virtual Python learning resources. Throughout his education and profession, Drew has nurtured a long-running passion for using and supporting open source tools and seeks to make it easier for others to use and learn them along the way. His cats are known for making appearances during virtual presentations, so keep an eye out for them. And lastly, some learning resources I'd like to point you to. We have Stack Overflow, as always, the Metpy documentation, and today's content on GitHub, which I will link you to in a second. And just note that if you copied the repository earlier in the day, you may need to do a Git pull to get the most up-to-date version. And with that, I'll pass it on to Drew.
Thank you, Julia, and I'll reiterate those last few things that you just mentioned as well. So to start, I will share my entire screen, and then I will take a second to zoom in on just Jupyter Lab so we can get to covering some things. So just a moment. Also, for today, the cats were locked out. I've had enough technical and internet outage issues to not have to fight them off for one virtual meeting. So not this go round. So with that, okay, please let me know in the chat or with a Zoom React if you cannot see my screen, and I will zoom in and make things more legible in just a moment. So as Julia mentioned, in the chat, you can find a link to the Project Pythia tutorials repository where this content is hosted. You can either follow along on your own computer, you can just watch me walk through it. You can also open our project in Binder if you click this link. This may take a little while to get spun up, so if you plan on following along using those resources, go ahead and click that button now. And also, if for whatever reason you aren't able to get set up on your own computer or use Binder, you can even just browse these notebooks as previewed in GitHub. So to get started, I'm going to be working from my own computer today. I am going to move into our tutorial directory. I've already installed the Conda environment that is provided for you today under environment.yml, environment.yaml. If you haven't already, you may need to set up this environment per the instructions on the repo, but I have it, so I'm going to activate it. Tutorial, if I can spell it correctly. And then I'm going to open up Jupyter Lab. Reminder, again, as Julia said, if you're working with these files on your own computer, we'll click this, and you have made a copy of the code earlier in the day or yesterday, be sure to get a more up-to-date copy of the code before following along. So I'm going to switch screen shares real quick to zoom in on Jupyter Lab. And we will. Boop. Okay, I'll make some more room on my screen in a moment. I only work from one monitor, so I tend to keep things oriented in this portrait mode so people can sort of drag and drop zoom around to be helpful for them. But please let me know in the chat or with Zoom reactions if for some reason this is not working for you. So the goal of today's Metpy tutorial is mostly to provide a whole overview of the honestly quite broad selection of tools that Metpy makes available to its users. I will sort of pick a section here or there to really take a deep dive into, especially when it comes to understanding how Metpy works with units and X-array data structures in Python. But otherwise, I mostly want to get the sort of reaction of, oh, I didn't know Metpy could do that for me, from people in attendance today. So with that, let's make a little extra room on the screen. Let's just give a quick introduction to what Metpy is if you're not familiar. And so, like I said, Metpy is a collection of a variety of tools. It is a Python library. It's been around for some time, created by fine people here at Unidata and sort of nurtured for many years to get to where it is today. It's built upon and next to plenty of other Python libraries you might already be comfortable with or familiar with, like X-array, SciPy, Pandas, NumPy, etc. And I've highlighted a few of those in this introductory notebook here. For this tutorial, I do expect at least that you know what X-array is, or at least what X-array data sets and data arrays look like, sort of netcdf-like structures in Python. And it will help, at least by the end of this, to have an understanding of how the Pint units library works, as nearly all of Metpy's functionality relies on unit awareness for correctness, for robustness, etc. So I've provided some links to a variety of overviews or tutorials that might help you with some of the topics that are important to understand Metpy's tools, depending on what you need Metpy for. So just a quick introduction. Using Metpy, importing Metpy is like any other Python package. Import it, take a look. It's there, it exists. However, Metpy encompasses a variety of sort of individual submodules and toolkits that we expect people to sort of access as they need. And so if I just import Metpy, I don't really have access to its full suite of tools. However, if we take a look at our documentation, which I'll be pointing people to a lot today and in the future, you can get a sort of overview of what these different submodules and toolkits within Metpy are. And so some of those you can see are our collection of constants that our calculations rely on, or the unit functionality, reading in files, etc. And so this might be more of what your importing Metpy will look like for your actual day-to-day work. And then we can see we actually find our calculation available to us. I'll be sure to sort of cover the variety of imports I'm relying on for each of the following notebooks from this point on, to at least let you know what we'll be working with in each one. So at the bottom here, I will scroll all the way down to the bottom of this first notebook, and I'll come back to this at the end. Our documentation has a variety of resources on its own, a hugely helpful collection of information, as well as you can see in this support overview link, a collection of ways to get in touch with us at Unidata with either questions, feedback, guidance for the project, etc. So this is the Metpy home base for getting things done. So if you're following along on your own computer or on Binder, you'll see we have 4 other notebooks I'm going to skim through today. The next notebook for reading in files is more of a quick demonstration to basically point out to you, hey, Metpy has this functionality if you need it, and so it doesn't look too scary if I need it for later examples. And then the bulk of this tutorial, we're going to focus on discussing units and X-array compatibility within Metpy. And then finally, with some time at the end, I may just show off a few calculations and interpolation tools, as well as, of course, meteorological plotting. And hopefully have some time at the end for any questions or making sure that we can help you get your work done with Metpy. So let's close out of the introduction. and we're going to be working from the file reading notebook. So as you'll see here, the submodule metpy.io contains a variety of tools for reading meteorologic data specifically. Notably, we can parse METARs or METAR reports for you and files chock full of them. We can read in, thanks to our community and thorough community contributions, GEMPACK formatted files, if you're familiar with these. This includes surface or gridded data and sounding data, again, in GEMPACK formatted files. We have some Nexrad reading functionality that I will at least introduce here, but may not cover in too much detail today, as well as a reader for Genie satellite imagery files. So for this file, I'm just going to bring in matplotlib to show a quick visualization at the end. Importantly, throughout this tutorial, I will be using the get test data function, which is sort of a internal Metpy function for pulling out data we use for examples in our documentation or testing our library. So please don't expect to rely on this to open up just any old file you have. But for the purposes of this tutorial, we can use it to pull out some example files included in Metpy. So let's import these tools. Luckily, nothing broke. If you're not familiar with what a METAR looks like, this isn't even itself what a METAR report looks like. A METAR report may just look like a foreign language if you're totally unfamiliar with it, but it's a lengthy collection of grouped characters and information reported by weather observing stations and radiosondes and the like. So a common format for surface observations from weather stations or from sounding launches and upper air observations. And Metpy can read in these files for you. So I'm going to pick a text file with some METAR reports in it. I'm going to parse it, and I will get back a maybe familiar for some of you. Just a moment. Pandas data frame with all of this information parsed into helpful columns for us. We'll be using this for some of the plot demonstrations later, but this is available to you. Also, something that may be used that I may touch on when we talk about units is that Pandas itself out of the box may not have support for the unit library we rely on. So we have a few we have a few tools to help you make information read in from a METAR report have unit information attached to it for some of our calculations. So that's just a quick demonstration of this. Then again, not much to show off here, but that you can read in GEMPACK formatted files into X-array data sets and data arrays using metpy.io. We won't worry too much about Nexrad demonstrations today, but you do have these tools available to you, and there are a suite of good examples on our documentation showing how to parse through our sort of Nexrad data structures to get the information you need. So let's skip a bit to the meat and potatoes. I'm going to close out of the file reading notebook. I'm going to skip ahead to the third notebook on units and X-ray. So if I don't get scooted to the end here, units and X-ray, a sort of core developmental philosophy for Metpy is that all of Metpy's calculations, or at least most of them, as many as possible, rely on well-defined quantities of information, meaning you have a number or an array of numbers with a certain magnitude, and you attach unit information to them. And we do this by relying on the Pythia library, if you're not familiar. This is a library built on NumPy and Python that allows attaching this unit information to numbers or arrays, enables a lot of conveniences for converting quantities from one unit to another allows dimensionally correct math to work out. So if you want to add together quantities with units, even if the unities may not, even if the quantities may not have the same units. So if you have something in, say, distance in inches and distance in centimeters, and you like to add them together, you can do that. You can do conversions, and Metpy relies on a lot of this functionality to trust the information you're providing us, massage any of these united quantities into similar values to get our calculations done and spit out something meaningful to you. So we can do all these sorts of conversions and cancellations necessary to do some of the complicated meteorological calculations we support. Metpy also now heavily relies on X-ray, which, if you're not familiar, is sort of a netcdf-like structure in Python, multi-dimensional labeled indexable arrays of information. And on top of that, if we use X-array and we use some of its functionality to preserve information, say climate and forecasting metadata attributes, we can enable even more conveniences within Metpy, or even some calculations that rely on a collection of these structures and information. So we'll step through some of these examples. We'll take a look now, and we'll get to X-ray in a moment. We'll start with the basics of Pint and the basics of units in Metpy. So you may find yourself performing, if I scroll down, this import a lot in Metpy. From the Metpy units submodule, you'll need the units class. This will allow us to create quantities with units. This will allow us to multiply a number or an array of numbers by a unit to get these values back. I'll show that off, but this is the important thing we're going to need to talk about units. And then later we'll talk a lot about X-ray. So let's import these. No errors, good time. Let's talk about Pint. So Pint provides us a collection of unit information, of a registry of available units, information about their dimensionality, what they're compatible with, et cetera, et cetera. It also, as stated here, understands prefixes and suffixes. So if Pint understands what a meter is, Pint will also understand what a kilometer is or what a nanometer is. And for most things, asterisk there, we'll talk a bit about later. For most things, using Pint on top of any old NumPy array is not a big headache. So let's walk through a few examples of this. Here, I'm going to take a quick NumPy array, 1 to 5, and I'm going to give the whole thing units of meters, and let's take a look at it. I've done this by just multiplying by units with the meters attribute. There's a variety of ways. If I make a new cell here, you can reference units within Pint. So you can use unit strings. So let's say hectopascal. You can, as shown below, use this sort of dot attribute notation. And so let's take our NumPy array, again, 1 to 5, multiply it by units of meters and see what we get. This is the Jupyter Lab HTML representation of a Pint quantity. So the two most important pieces of information for that are the magnitude, or the values themselves. We did 1 to 5 here as a range, so 1, 2, 3, 4, and the units on that quantity, in this case, meter. Sometimes it may be important to construct this manually using the quantity, the units.quantity constructor. We'll talk about some of the hangups near the end, but if you need to be careful and you need to be certain for some reason of what you're making, or especially if you're working with NumPy masked arrays, you may need to explicitly construct quantities in this way. So I've created a new range of numbers. I've called it time, and I've wrapped it in this quantity constructor where I've given it the magnitude of the values that I want my quantity to have, and then the string of the units I want to attach to. So once again, we have our magnitude of 2468 and our units of seconds on this. You can sort of do this in line. You can stack these one atop another to create sort of more complex unit constructors. So here, say we want to define gravity as 9.8 meters per second squared. And so I've done that very explicitly. You also can use Pyth's strings to sort of create more complex units under the hood within a single string. So here I've said I want to give my value of 9.81, the units meters per second squared. Same deal. Now, importantly, where we can go from here, we can do operations with units. We can do math with units attached, and Pyth can do the work to make sure that these are interoperable or give us new units from compounding mathematics under the hood. So let's say we've created our distance up above and our time. Our distance had units of meter. Our time had units of second. And so if we divide distance by time, we get a brand new quantity with a magnitude of element-wise array division. So we divided one element by the other, so on and so forth. And now we have a new unit of meter per second. This works just fine for multiplication and division. However, of course, if you're trying to add two numbers together and subtract two numbers, they need to be not necessarily identical units, but at least the same dimension, the same type of unit. So in this case, we can add distance and distance together because they have the same unit of meter. But if I try to add distance and time, Pyth will not be pleased with me. Cannot convert meter to second. So Pyth tried to find a way to make one of the units or one of the quantities have the same units as the other, and unsurprisingly, it failed. Note in this last example, though, that if you don't have identical units, but they are at least of the same dimension, the same type of unit, it will work. And here it just converted our centimeters into inches and did the math for us. Now, either for your own usage, just understanding the quantities you're working with, or if needed explicitly under the hood for some of our calculations, Pyth has a sort of robust suite of tools to convert one unit to another. This can be done explicitly to make a new quantity. So in this case, I'm taking a quantity of 1 inch. I'm converting it with the to method, .2 on the quantity, millimeters. Again, defining units either with strings or this unit attribute notation. And so here I've converted 1 inch to millimeters. If you have a variable containing a Pyth quantity, you can also convert things in place, meaning that you don't have to assign it to a new variable. This, of course, can be potentially dangerous if you're not careful, but if you know that that's what you need and you're not looking to assign new variables, I can define a quantity called A, give it a magnitude and units, and then I can, with the I2 or in place to method, I can convert it to feet, and I've not given this a new variable. Just give me A again, and sure enough, we have units of feet. For a variety of either, again, understanding complex units or for use in calculations, whatever reason, Pyth also has routines for simplifying units. So here I've defined this quantity LF as 3.34 times 10 to the 6th joules per kilogram. And now if I want to reduce this to its base units, let's take a look at both. This top here is as I've defined it, units, joules per kilogram. And here Pyth has reduced it to the identical dimension, but base metric units, meters squared per second squared. Similarly, most Pine operations have this I in place operation available. Now, Pine may not do some of these simplifications on its own, depending on what unit systems it is converting between. So if we take a look at this calculation where I multiplied a length in inches and a width in centimeters, it's given me a new unit of centimeter inches, which is not wrong, but also is not particularly helpful to many people. So in this case, if you know, all right, I need this in square meters, that's what I'm working with, we can convert that and see what that looks like. So why does this matter for Metpy? Now, again, nearly all of our calculations expect these quantities as inputs to the functions. So if you want, in this next cell, as an example, to calculate dew point, given relative humidity, we need to know the units of relative humidity to give you the correct answer back. So if I change up this cell for a second, let's get rid of this. I'm commenting out my units. I've just defined a temperature of 73.2. Who knows what that is, but that's what it is. And a relative humidity of 64. If I try and calculate dew point from this relative humidity, given this temperature and relative humidity, you will get a helpful value error from Metpy. And a little hint that any of your numbers or arrays can be given unit information using the information I gave you above. So either multiplying by units or explicitly constructing it with this units.quantity. So let's go back up. Let's see if I can unbreak this. If I multiply each of these values by their appropriate units, so I'm specifying, here we'll split up these cells real quick. Let's take a look at temperature, relative humidity. Now I have a temperature of, instead of just 73.2, 73.2 degrees Fahrenheit, and a relative humidity of 64%. Now for some of our calculations, percentages and fractions can be used interchangeably, but most of the time it is safest and most effective to just explicitly define your units. So now with my new temperature and relative humidity, will I get yelled at again? I won't. I've calculated dew point from these values, getting a relative humidity of 15.7 degrees Celsius. And again, if I'd like, I can take this dew point, I can convert it to, say, degrees Fahrenheit. That is 60.3 degrees Fahrenheit dew point. Some notes here that I can provide more information for people at the end of the presentation. Headaches you might run into here include that masked arrays, NumPy masked arrays, notably, historically, have not played well with pint quantities, or at least with unit multiplication of pint quantities. And so you, especially if you're used to using, say, netcdf for Python, which gives you a lot of masked arrays in your variables, you may run into headaches with that if you don't explicitly use units.quantity. But if you use that, you can avoid many headaches. Sometimes in the past, well, even to this day, multiplying units on the left or on the right of a value in pint can have an effect on what your final data type is and what your final value looks like. So again, if in doubt, just manually create the quantity. Also notably, something people run into with Metpy is that the MB unit is a standard unit already in the pint unit registry for, I believe, millibarns. And so if you're trying to use millibars with Metpy, use MBAR, MBAR. But you'll see this in plenty of places on our documentation. You can also specify hectopascals, pascals, whatever you're using. So we'll pause there and we'll move into the next most important thing to discuss, and that's how Metpy relies on Xarray for making your life easier, or in some cases, making some of our calculations or functionality possible at all. So I definitely want to take a second going into this to also acknowledge the variety of projects in this space that are either building even more on this functionality or sort of taking their own direction with tools like this, like say CF Xarray. But basically, Metpy has, through some very helpful community contributions, created what are called Xarray accessors on the Xarray dataset and data array structures, meaning that if you have an Xarray dataset or data array and you have Metpy imported, we can provide some unique Xarray functionality on top of these data structures. Some of our calculations rely on these, or some of them are just simplified by having these available to you. And so we'll introduce those real quick. Let's scroll down and focus on this section. Notably, the main areas that we look to help you here, if you have Xarray data sets and data arrays, are we want to help you understand CF convention metadata that adheres to climate and forecasting conventions, particularly in the grid mapping arena. So if you have a CF compliant netcdf file and thus Xarray data set that you've read in, we can say, understand the specific projection information of your data and provide you shortcuts to Cartopy or to PyProj that you might already be familiar with using, but maybe you don't want or aren't able, or it's not convenient to manually construct the relevant projection information in these tools every single time you work with a new data set. Also, we look to take Xarray attribute information for, say, units and give you shortcuts either to pint quantities or do that for you behind the scenes and take the information from the Xarray metadata and understand the units and put them in the right place for you for a variety of calculations. So let's start by opening up an Xarray data set. You may be familiar with this. In this case, we're using some GFS output, a netcdf file. This file contains a variety of dimensions, coordinates, and data variables within it. And we can see that summary here. We won't worry too much about everything available here, but we will come back and refer to this data set a variety of times. First, for a few demonstrations, let's just pull the temperature data array out of this data set. So let's scroll down, take a look at that. Our temperature on isobaric surfaces here has 4 dimensions. We got time, we got vertical levels, got latitude and longitude, and if I click here, a variety of attributes attached to the data array. If you use Metpy's dataset and data array accessors, we can help you avoid some of the frustrations that come with using meteorological data formats or with using, say, model output, where maybe picture a time, I don't know, two code cells ago, where I was looking at information and I had multiple pressure coordinates for different variables in my data set. And they have maybe not particularly helpful names like isobaric 1 and isobaric 3, which is on its own maybe not particularly helpful to me. So if I scroll back down, Metpy can help you try and avoid having to remember these, dive into it every time. We can give you shortcuts to finding the coordinates within your data set in sort of a reproducible and accessible way. So if we use CF metadata and the names that a variety of these coordinates are sort of allowed to have or suggested to have, these coordinates including time, vertical coordinates of pressure or height, latitude, longitude, X and Y, projected space, etc. We can try and reference the coordinates within your data set or data arrays with more sensible names. So here, without knowing exactly what the name of my time coordinate is in my temperature data array, I can use .metpy, which in this case is how we get to the Metpy X-array accessors. These are available to you if you've imported anything from Metpy. So .metpy.time. So if I run this, it's pulled out the time1 data array. I didn't know that it was called time1, time3, whatever. But this found and correctly guessed my time coordinate for this data array. So we can give you some help, give you some shortcuts for working with, say maybe your time coordinate changes in name depending on what data you're reading in. We can give you some convenience here. You can unpack this for multiple coordinates at once if needed. So here I'm using .metpy.coordinates, and I'm giving it multiple variables that I want to unpack into individual data arrays. So I'm saying find me the X coordinate and put it in the X data array, find me the Y coordinate and put it in the Y data array. Take a look at X. In this case, it found my longitude coordinate, which is the sort of X information on my current data array. So using these sort of guessed names based on CF metadata, you may also be familiar with xarrays.sel or .loc, .select or .locate methods for sort of subsetting, slicing, selecting subsets within your data. And so if you use the, let's go through here, .metpy accessor here, you can select based on these common names instead of having to remember, okay, do I need to select based on time1, isobaric 3, etc. In this case, I've just told it I want to select on my time coordinate, whatever it's called, using a vertical value of 50,000, whatever that means. In a moment, I can also show off that with this interface, we can allow you to subset and index using units. And so you may have vertical pressure coordinates in Pascal, but you'd like to get the 850 millibar level. We can sort of do this under the hood for you to help you find information within the same dimensions, but perhaps with differing units. So let's take a look at this. Take a look at heights. And sure enough, within my original data set, if I took a look at the geopotential height data array, I used .metpy.cell, which notably geopotential height had a different coordinate than my temperature data array above. Find the time coordinate, look for this time, find the vertical coordinate, look for this value. And sure enough, I now have a surface of geopotential height at the 500 millibar level, at this given time. So we've shaken off two of our dimensions here. I may speed up a bit through some of this so we have some time to show off a few cool calculations and plots and still have questions at the end. The next important thing that Metpy enables on top of Xarray is an understanding of your grid mapping or coordinate information for your data. So a common tool you may find yourself using here is the .metpy accessor, again, parse CF function. You can apply this as shown here to an entire data set. You can, on an entire data set, pick out individual variables you want to parse, or you can pick even just a single variable that you'd like to parse. So let's run through these, but let's also take a look at just the relative humidity data array after I've parsed it using .metpy.parsecf. So things look pretty similar here so far. However, you'll also notice now a new coordinate has been attached to this data array, and that is the Metpy CRS coordinate. It's an object. This object contains a variety of information and methods within it that we can talk about in just a minute. But this is our sort of pipeline to making Cartopy and PyProj work with your metadata in your data set more smoothly. Note that if you don't know, don't have, or for whatever reason need to assign CRS information to your data set or data array, you can do so, and you'll still get back this Metpy CRS object that you can work with to get out helpful objects moving forward. And some of our calculations rely on this Metpy CRS. So you may need to manually attach this projection information if for some reason it's not available in the metadata. So the important things that you can pull out by hand for this are, now that my relative humidity has been parsed, it has this Metpy CRS object and its coordinates. I can use .metpy, again, the accessor always, .cartipy CRS to pull out a pre-made cartipy CRS object generated from my projection and grid mapping information. You can use this for plotting, transforming your data, etc. Similarly, if you're familiar with PyProj and interface to Proj, you can get out a PyProj CRS from our Metpy CRS object. This may be helpful for transforming points or doing, say, great circle calculations, which we do rely on this for, say, our cross-section calculations, which I'll show off in just a second. Now, to tie it back to the beginning, we still need unit information for the variety of our calculations to work. And while this may often be attached to X-array data sets or data arrays through the attributes, through the metadata, we can also sort of more directly control this behavior. If we say, here, I will show this off to begin. To let you know, I'm again using the Metpy accessor, this time the Quantify method. Sounds familiar. It's because we, under the hood, want a quantity contained within this data array. So now, instead of just relying on an array of values within my X-array data array and a text string and the attributes saying what the units are, and the potential for these to get mismatched, I now have contained as the actual array of information within my data array, a pint quantity. And then a layer below that, that pint quantity is just two things, a NumPy array of numbers and the unit itself information. So this is helpful and necessary for a variety of our calculations. You also can then perform some of the usual X-array methods that you're used to directly on your data array. So if I'm going to show you heights again, it still has this pint quantity under the hood. So I'm going to delete this cell. Let's take a look here. Good old X-array mean. I want to take a mean across longitude for my data array. If I were to do this or do some sort of calculations on my array without attaching unit information to it, there's a chance things could change without me appropriately recording it. But in this case, here I've preserved my unit information. I have these in meters, it's recorded, it's attached to my values, even though I've performed this mean across my data. There are limitations to this that are covered well in the documentation, notably that if you're used to relying on X-arrays lazy loading or say DAST, this Quantify will explicitly load your data into memory. So watch out, be careful. Importantly, having a pint quantity as the actual information contained in your data array might not play well if, say, you want to save this back out to an .etcdf file. So we've included a way for you to sort of strip the units, de-quantify, so to speak, the underlying pint quantity back to a NumPy array, and make sure that you record your appropriate unit information after any conversions or calculations have happened. Some other particularly helpful unit shortcuts we give you are that, again, if you're using .metpy.cell or .loc, select or locate, you can give it pint quantities specified through the unit multiplication I showed off at the beginning, or by manually constructing them, whatever works for you here, to index your data along united information. So again, say my vertical coordinate, what if my data array had it in pascals, but I knew I wanted the 300 hectopascal level. This will understand the unit information under the hood for you and sort of find what you need in your particular units. We also can convert the units of, let's come down and take a look at this, of your values within data arrays for you. So if you use .metpy .convert units, it will figure out what units your data are already in and convert them for you. And you can do this for your coordinates, so on and so forth. Importantly, if you were to quantify your data, excuse me, and have these pint quantities sort of under the hood there, you might be used to using, say, data array.values or .data to get out your underlying information. If you use this, you'll still get the NumPy array sort of down at the bottom of everything. But if you use .metpy.unit array, we can give you a pint quantity on its own from your xarray data array. And so I'm going to take a second to skip through this to come down to a quick demonstration, set down to where we've got CF compliant data set example of how this can make your life a little easier, even behind the scenes without knowing some of these shortcuts and tools along the way. And that is that many of our calculations, especially those that need to be aware of the, say, grid mapping information of your data, can look for a variety of this information that we're parsing and understanding in the background, sort of behind the scenes, and make your life a lot easier in doing certain calculations. So let's demonstrate that real quick. I'm going to open up a data set of NAR data, NARR, the North American Reanalysis. You'll see a lot of dots, a lot of parentheses here, but the usual open data set to get an X-ray data set, this is where I'm just giving it the file path to my test data. And then all in one step, I've decided I want to go ahead and use Metpy parse CF to understand the coordinate information within my data set. And then I'll show you that for some of our calculations, it's important to sort of promote latitude and longitude arrays to X-ray coordinates to enable some calculations. Then I'm going to take a subset of this data set. I'm going to use .metpy.cell to find the 850 hectopascal level on my isobaric coordinate. And then I'm going to use squeeze to just get rid of some superfluous dimensions if they're hanging around and not helping us. And then finally, to make sure that I preserve my unit information, I'm going to go ahead and quantify this and get out a, if we take a look, excuse me, data set containing multiple variables, each with a pint quantity under the hood. And we have selected our data at the 850 hectopascal level. Now, if you've used Metpy in the past, let's take a look. Let's say that I've come at this from a different direction. This cell, I'm just creating a variety of individual quantities. Let's say that I just read something in from a netcdf file using netcdf for Python, took out each individual variable and put it into its own quantity one at a time. Let's say I've done that. This is what my temperature quantity looks like. Now, I know that if I want to calculate advection, say, I need grid information. So I'm going to check the documentation for Metpy's lat-long grid deltas. I'm going to need some longitude. I'm going to need some latitude. I pull those out of my file. I'm going to need to make sure I understand the dimensions. Is this ordered Y and then X or X and then Y? And then I'm going to need to calculate these grid deltas. So let's do that. Let's get a dx and dy. Okay, so I got my dx and dy. Let's double check the documentation for advection. So for advection, I got to figure out what I'm advecting. I got to give it my winds. Then I got to come specify my dx dy to tell it how far it's moving. So let's fill all those blanks in. And I've got mpcalc, metpy.calc, advection. I got my scalar I want to advect. I got my wins. I don't have any W. Maybe I didn't have to specify this, but I wanted to be careful. I've specified my dx. I specified the dy I calculated. There's no dz to worry about. I double checked that my dimensions, my x dimension was my last dimension. So I gave it a -1. I did my homework here and I came to this final function signature to get advection of my temperature with my wins given my grid spacing. Or if I double check my X-ray data set called subset that has this Metpy CRS information attached, it's got X and Y, latitude and longitude. And I just say, I want advection of my temperature given this U wind and this V wind. A little heads up to make sure that you're not accidentally letting some, say, Z dimension slip in that you weren't thinking about, or that it's telling you what order it was looking for them in. But sure enough, bam, voila, we have ourselves a advection calculation without having to sort of spend so much time picking out the individual pieces and parts to make sure that this works. We're just able to understand the appropriate metadata under the hood, behind the scenes, and take care of this for you. A quick heads up that I mentioned before, we provide this dequantify, and you may end up having to get rid of the Metpy CRS coordinate because that won't exactly end up in a netcdf file smoothly. If you find yourself wanting to, say, save out this analysis that I did. And this is on the documentation. We won't worry too much about covering it here, but I've attached it if you are working through this, where if you don't have CF compliant metadata attached to your X-ray data set, you can sort of create the appropriate CRS information to attach. And then these calculations will still work for you. So that was the bulk of what I wanted to cover in the tutorial. I'll spend the next few minutes just sort of showing off a few other tools that Metpy has that you might be able to benefit from using. And then I want to make sure to save a few minutes for questions and help that anyone may need. So we're going to close this. We're going to take a look at some calculations. The fourth notebook here. This is a huge suite. I haven't even decided to, particularly show off many individual calculations that we didn't cover in the previous notebook. But notably in metpy.calc, we can help you with a variety of meteorologic specific calculations, including dry thermodynamics, moist thermodynamics, sounding calculations, and various indices on soundings. We can do some sort of base level maths and say derivatives across grids, things like that. A few operational indices, some height and pressure, standard atmosphere type conversions in math, a big suite of smoothing and filtering tools, and some less well categorized tools available to you. So we'll scan through the imports here. If you're viewing this notebook, these are links to the documentation with more, with lists of these calculations available to you. So if I take a look, huge collection of calculations you might benefit from using. Similar for our suite of interpolation tools. These are generally built either on sort of our own implementations of certain interpolation routines or on SciPy or on SciPy. Really quick, something that you can only do with a X-ray data set with appropriate information attached and parsed by us are cross sections. This is tied to an example in our documentation, so I'm just going to skim through this. But basically, if I have a data set, I parse it, I tell it my starting and ending coordinates that I want to do a cross section. I use Metpy's interpolate.cross-section to perform the math. And then I'm going to find potential temperature on my at my cross-section points, as well as relative humidity, and to get some sort of winds in and out of my cross-section. So we'll take a look at that. We see we've attached a few new variables to this data set, And then finally, let's take a quick plot to look at a cross section. This particular example has a map showing you where the cross section begins and ends, as well as the cross section itself, with winds, contours, and colored contours, colored filled contours plotted along the cross sectional path. And then finally, of course, Metpy has a suite of plotting tools that either create particularly unique plots that are not easy to recreate alone in Python, including SKUTs and hodographs, or station model plots, the ever popular, if I skip down, station model. We can take a quick look at these. Basically, with both SKUTs and station plots, you will sort of create an object with information about, in the SKUT's case, you just create the SKUT object and then can add plots or particular, say, background lines onto the SKUT. Or for station plots, if we scroll down, in this case, I'm pulling in some of my METAR data from early on. Given it, once you create this station plot, you can attach a variety of parameters and locations and sort of customize your station plot to either fit, a standard product you're showing people or sharing with people, or sort of make it your own. If you've attended some of our workshops, you might have seen how we tweak these a bit. And then the other tools that our plotting sort of suite provides to you are maybe conveniences or a collection of tools that make plotting perhaps a bit quicker, easier for exploration, or more accessible to people coming from other plotting interfaces in the past. And that we call our declarative plotting interface. I'm going to skim these through to the end, make sure we have a chance to actually look at these. But basically right here, I've recreated my station plot from above, but with this, as we call it, declarative plotting interface, where we can go through, pick out individual attributes, tell it what these are supposed to be, and you give me the plot, right? So I tell it what I want to plot, I tell it at what time, I tell it what fields, I tell it where at, and it will do the matplotlib wizardry under the hood to get me a nice station plot, a nice plot of station models for surface observations. And then finally, a quick shout out to a contribution from one of our interns last year, a community contribution to expand this plotting interface to support GIS data. So the particular example here is using GeoJSON. And in this case, we are looking at provided outlooks from SPC. So if I scroll down, we were able to just specify what products, what colors these various fields are supposed to have, and we were able to plot a day one convective outlook with the provided GeoJSON file from SPC. So I haven't left much time for questions or clarifications here at the end, but I'm glad to hang around a few minutes after, or to once again, if I close these out, to pull up our collection of ways to reach us, make this available to people at any point. So thanks for listening. And like I said, I'm glad to hang around for questions here at the end.
Thank you, Drew. That was great. Again, like Drew said, put any questions you have in the chat and we'll hang out for a little bit to answer them.
Yes, I will drop some of these in the chat now. Importantly, you can reach us at our GitHub Discussions for any sort of open discussion or Q&A, or get help with any issues you're having there. Through our GitHub, you can also report issues or contribute to our project if you'd like. We also have avenues for sort of text chat or email support as well. And I think we keep pretty busy on Twitter too. So a variety of ways to get in touch now or after. Thanks so much. Appreciate the feedback in chat.
Thank you. Bye.